Hello Paul and all the community of developers following Paul's most excellent series on Raspberry Pi and driving LEDs with GPIOs and PWM for pulse width modulation, which emulate analog voltages. And the deal here was to manipulate our 3-color LED, which I remind you that I use a common ANODE RGB LED. The circuit doesn't change. I still have the same. There's no need to change anything. So just for reminding you where we stopped on the previous video, where we just toggled on off our 3 colors with the 3 push buttons here. So it's just the same wiring. I didn't touch the board at all. So what I had to do was to adapt a little bit my code. I started yesterday with a object-oriented approach with a class, a generic class for component and a component list. What I will do this time is that I will use a specialization of my component list to create an LED specific class, which will be able to manage the brilliance of the LED related to the level input will increase with the button. So previously we had a class here which was component here, and now we will use what is called inheritance. Okay, so we will create here an LED class that inherits the component class. Remember that in component class we previously had a color and pin properties. Now for the LED I will add here brilliance, max brilliance, which will be, as you can guess, maximum brilliance, and PWM, which will be the pulse width manager modulator that will be attached to this LED. For friends, developers and architects, I agree that this will create a strong dependency on something that's not directly related to the LED class. Could have used dependency injection or strategies or whatever, but I prefer to give priority to the simplicity of the code, readability of the code for now. We can go further afterwards. In the LED, I will have here methods. One method for going up. This method will manipulate the brilliance. Okay, and a method to update. The update method here will be used to effectively update the duty cycle on the related pin. Okay, so as a documentation I can say that up here will act on brilliance and update will act on a duty cycle. So we can say more or less that the up method will only act on a logical state of the LED, and a duty cycle will update the real world based on the logical value of the brilliance. That's more or less what I will show you here. And now the code. You see the board didn't change. I will put the board out of sight here for the moment. It will give us more space to see what we are talking about. So, once again, I remind you that we are with a common anode RGB LED, which can be different from your LED. Okay. The component didn't change and will serve as a base, will be the base class for the LED. The class LED here inherits component, which means that everything already defined in the parent class, which is component here, doesn't have to be defined once again, of course. Okay, this is the constructor, kind of constructor here. So it's the method that will be called at initialization of the class, the instantiation of the class. It's not exactly a constructor, there's another constructor more specifically acting like a constructor, but this method will be automatically called when you instantiate your class LED. And if you want to transmit the values to the parent constructor, you can call it here. Okay, we instantiate this with the same parameters, pin and color, so there's no change, but we initialize here in properties, as we said, brilliance, max brilliance, and PWM. At the beginning, PWM is set to none because I don't want to abuse resources, and I won't use PWM if the LED is off. That's my idea. Okay, off is off. There's no need to make it more complicated. Maximum brilliance is to 256. And at the beginning, the brilliance is set to 0. Everything is off. Okay, I told you that there would be a up method here. For the details of the algorithm, you can go back 2 lessons back, where we managed a LED with push buttons like this, and I had used binary bit shifts to have an exponential variation. So when we try to increase the brilliance, if it's the first time, the brilliance will be 0. Okay, so we check if the brilliance is 0, then we will try to initialize the PWM object of our GPIO library. And as you can remember, we have to give here the pin on which we want to associate this PWM and the frequency. Previously I had some flickering problems on the camera. It was not visible with raw eye, but with the camera the frequent flickering because I had chosen a 50 Hertz frequency, and as our dear colleague Kate suggested, increasing the frequency has made disappear the flickering. So thank you, Kate, for your suggestion. And yes, maybe some cases where the PWM could always be already be started, so we do this in a try except here, just to be sure. Okay, once the object is instantiated and affected to the property PWM here, we can work on this property. Property is just like a variable, but which is attached to the instance. It's also called an instance variable. Interest of this approach is that each instance can use the same name of variable. You don't have to have a PWM 1 or PWM red, then green, then blue. It's always PWM attached to the current object. Okay, so when this is started, instantiated, I mean, we can call different methods on it, like method start here. Self PWM start will start the pulse width modulator with a value of 100, which is the duty cycle. Usually, you remember, we start with 0 meaning that we have a 0 duty cycle, which is no signal. But once again, I must insist that we are here on a anode, common anode, with a positive 3.3 volts on the anode. So if you want an absence, total absence of difference of potential voltage between anode and cathode here, you have to inject 3.3 volt. Delta will be 0, and the result will be no signal. Okay, so if you want to increase the brilliance, you have to decrease the voltage here till 1.5 volt, for instance, and then you will have your delta here, which will be 1.5, 1.8, but you will have a current flowing from the anode to the cathode. Okay, there's a difference. That's why we have to start here with a maximum value of the duty cycle. Okay, and we can record here the brilliance, which will be the logical value of the brilliance here of 1. Okay, there is another specific case, particular case, that this brilliance could be at its maximum already. Paul, you asked us to cycle, which means that when we reach the maximum brilliance, next step will be back to 0. Okay, so when we have reached here the maximum brilliance, and we want to increase once again, because we are an up method, then we just turn the LED off. after maximum, the next step is off. Okay, off, it means that we will stop our PWM and then set it to none, which frees some memory. We can also set the state to 0. State is a property of the parent class of the component, and we can set the brilliance to 0 too. All this means that we turn off the LED. And we have a message here to show us that we stopped this LED. As first particular case here, we are off and we want to turn on. Second possibility, we are maximum on and we want to turn off. Else it's all the other steps, all that is between 1 and 256, and then what we want to do here is to change the brilliance and increase it with the bit shift operator as we did before. If you want more details about this, you can go back to the other video just before. Okay, for the down method, I won't use it here, but just a placeholder for later. What we want to do here is implement the update method. So this update method will be used to send the good signal based on the logical brilliance of the current component. Okay, and we do this only if brilliance is above 0. There's no need to make a whole treatment if the LED is off. Okay, so if the LED is off, if the brilliance is 0, we will just set the output to true. Once again, maximum current here, maximum voltage, so that the difference of potential will be 0 and the LED will be turned off. Okay, between the two we calculate the duty. So the duty cycle will be the brilliance on 256 in percentage, so by 100. And as Kate suggested me the other day before I started with this, when I realized that I was working with a common anode LED, we have to invert, which means that when we want very low brilliance, we have to send a very high duty cycle, because the difference will be minimal. Okay, so that's why we subtract from 100 here, and then we just adjust with a self PWM, change duty cycle and duty. Okay, how do we use this now? Component list, I'll let you see the previous video for this. When we push components in the component list, we don't instantiate component, we instantiate LED, which inherits component, of course. Okay, this will allow us in the button event handler to call the method up when we press a button. So the event handler just changes the logical state of the LED, the logical brilliance of the LED. That's it, that's all. And in the while loop, all we have to do is call update method on each LED of the list. And the update method will update the PWM duty of each LED based on the logical state of the LED. Okay? Does it work? Maybe. So, I'll launch the code here. It's off. I'll press the red. Okay, very small signal. Press again. Maybe I can see. Oh no, that's not this. Try to show you. The begin messages. Okay, 98% brilliance 4. Once again, 97%, 94%, 16, 75, brilliance 64. See, the brilliance is following the binary shift. And 256, red duty 0. Then off. Okay. Same with green. Same with blue. Green off. Red off, and you have full blue. Okay, so that's also an illustration how objects can be really useful and practical to organize the code and make it easier to make it evolve, in my opinion. It asks a little bit more work at the beginning, but after this you can enjoy it. So thank you for watching. See you soon. Bye. Cold coffee.